Hey everybody, and welcome back to Algebra 2 Online. So today I want to take time to talk about some what we call special functions, specifically piecewise functions. So they're called piecewise because you can see, like this example, they're made up of different pieces, right? And this is actually a very famous function, used a ton in computer programming. A lot of economic models follow this, but it's called the greatest integer function, or sometimes it's actually got a few names. I should probably put the other ones here too. So it's also called the step function, which I think is kind of obvious. And another name for it is this is probably the most common one, honestly. Like, this is its true name, but the floor function is what we use all the time. We're just kind of talking about it in like computer science. And basically what this thing does is it just outputs the word, I don't have enough room here, so the greatest integer that is less than or equal to whatever we plug in. And you can see it. Basically, you're only ever getting integers, right? 0, 1, 2, 3, -1, -2, -3, so on. And this does just continue. It goes like this forever, and it goes down forever. Seems kind of weird, but you do this like double bracket to denote it. Sometimes we might also say, like, if I take this example here, I could also say what's the floor of -2.7. If you type that into something like Desmos, it will actually tell you what number that is. It's an actual number. And I think to at least see the first few of these, it helps to have like a number line to kind of go off of. So if you have, let's do 0, 1, 2, 3, that will be -1, -2, -3. And if I'm going to say this is like 1.3 or so right here, this little red dot, the greatest integer that is less than or equal to that would just be 1, right? Basically, it's like a round down function. It just kind of takes this, chops off the decimal, and rounds you down to 1. If you were at an integer like 0, you're just going to always get 0 back out. So if you're at anything like 1, you would just get 1. If you're at 2, you get 2. If you're at 3, you get 3. If you're at 0 right there, right, you get 0. Negatives are kind of harder sometimes to think about. So if you're over here, like let's say that is about -2.7, you can see that the output, the answer here is -3. So it will always just go down. So it says up here, the definition says the function outputs the greatest integer less than or equal to the input. A lot of times at -2.7, students want to give it -2. But that's bigger than, that'd be rounding up, right? So if you're here, you actually round down to -3, and that's why you get that. That can be kind of weird. And if you think of bigger numbers, you're always rounding down. So -99, right, would be bigger than this number. And so we would have to actually go down more until we get to -100. That's what that would equal. And just to do another big number one, basically what this thing is doing, right, is it's just chopping off these decimals. So when I had 0.999, I could have even infinite amount of 9s there. It always just chops that off there and rounds down. So 879 is what that thing would equal. But that is a floor function, and it is really just a special kind of piecewise function. And these show up all the time. This is like a lot of economic models do this because they might charge just a flat fee, like, I don't know, like for the first hour of service for some company, they might not charge you, but then if they are working on something for 2 hours, then it jumps to like $100 an hour, let's say, or something. And then if they're working on it for 3 hours, then it jumps to just a flat like $200 for that time. So even if they did like 2 hours and like 50 minutes of work, like over here or something, then you're still going to jump and they're just going to like charge you a flat like $200. But as soon as they work over maybe 3 hours, then you're going to get like charged $300 for that time or something. So we'll see these actually a lot this year. They keep showing up. They show up in pre-calc and calc and things down the road too. Another one that's really famous is the absolute value function. So a lot of people don't realize that actually the graph of this thing is piecewise. So if you've never seen it before, this is actually the definition. And a piecewise function has this weird like bracket setup to it. So I'm saying absolute value looks like x if x is greater than or equal to 0, and it looks like negative x if x is less than 0. And if I was going to graph this thing out, I'm going to just take some numbers off. So let's assume these are all like ones here. So if I was going to graph this piece, okay, I need to graph y equals x if x is greater than or equal to 0. So greater than or equal to 0 is just from this line over, right? These are all the things that are greater than or equal to 0 over here. And on that side, it's just going to look like, so this is 0. It's just going to look like that, right? It's just a piece of the line y equals x. The other piece of this graph looks like negative x. And negative x, right, just is the diagonal line that goes downhill, right? And we are graphing that for every x value less than 0. So negative 1, negative 2, negative 3, all these x's in here that are less than 0, it's going to look like negative x. Really, there's an open circle right there that overlaps with the green, and that's because of how the inequality is. So it's equal to it here, but not equal to it down here. So really, when you look at the graph, if you go type it in somewhere to like a graphing program like your calculator or Desmos, you just don't even see just like a jump. Like here, there were definitely jumps in the graph. But here, it's just connected. But that is actually another piecewise function. It's a very famous one. They really do look like this weird V thing. Basically, what the absolute value does, right, is it takes the line here, and it just makes all that stuff positive. It almost like bounces all these negative values up into the positive. So it's kind of like a reflection where you just reflect these values that would be on this line up into where the purple is there. So I just wanted to do a kind of more tricky one, I guess. This problem has like a few parts to it, and hopefully, now that you've seen that last one, this will start to make some sense after you see another one here. So if I was going to graph this thing, I'm going to do this in yellow, and I'll do this one in green. The way we read this is that the function looks like x plus 5 if x is less than 2. And then the function looks like x squared plus 2x plus 3 if x is greater than or equal to negative 2. So there's sort of like a hidden if kind of statement in there. So the part over here is just telling me where to graph these two pieces, right? You know, this first part is a line, this part's a quadratic, so it's going to be like a curve, right? So when I get my final graph over here, it's going to have very distinct pieces, like a linear part and then a curve. And basically when I graph these things, I actually look here first. So I would go to -2, and so at -2, right, it's like I'm going to test what -2 into the line would look like, right? So I'm plugging -2 in for x, and I get 3, right? But because it was less than, not less than or equal to, I know at -2, it's actually not going to equal 3. It's going to be an open circle there. So that's how I got that. And then this is just like Algebra 1 stuff. Like I know the slope of this is 1, right? So I know that I need a line with slope 1 kind of coming from the left side, right? Because it's less than it. So over here, it has to have a slope of 1. So I can put in like a dot or two and then just kind of do that. And that would be the first piece, right? To do the second piece, I can go and I know that this one is actually going to be defined at -2. So I can go plug in -2, and I would get -2 squared plus 2 times -2 plus 3, which would be 4 minus 4 plus 3, or just 3. And if I go and plot that, then I know at -2, it's going to equal 3 right there. Okay? So that's kind of like how in this last problem we filled in that point. It's kind of what happened again there. And you could just try to plug in more points over here if you want and just like connect the dots. I'm going to actually use this time to just kind of quickly review a little bit about quadratics. We're going to talk about them a lot more. But one of the things that I do hope you remember from Algebra 1 quadratics is the line of symmetry. So -b over 2a is an important formula, I guess you can call it, that really finds the line of symmetry for a quadratic. So all quadratics are kind of shaped like this, and it would find that middle line of symmetry. And in this one, right, if I plug in -b, which is -2, and a is 1, I just get -1. And then I know that now, like, the the function has that, like, dotted line there as a line of symmetry. And so I could just go and plug in -1, and I would find out what the output is. So f of -1 is just 1 minus 2 plus 3. Plus, why doesn't that run? All right, there it is. Which is going to be 2. So I know that this point is on the graph. And I can just use symmetry because what the line of symmetry will help me do. I know that this point then has to be on the graph, right? Because if this is here at -2, 3, then this has to be here on the other side of that line of reflection. So then you can kind of just like connect it with like a little, curve as best you can. And that would basically be the piecewise function. You had this one piece that really started with an open circle and went down. And then you filled in that open circle. And then you have this like curve that fits like a quadratic shape. But it wouldn't graph the part up here because that piece over there is not in the x bigger than -2 area. So I just want to answer these next questions. So we have a question, is what's the domain? So there's no jumps or anything. The domain is one of those all reals. The range is actually the same thing. Like you got arrows going up and down. so that's also all reals. Passes vertical line test, so yes, it's a function. Continuous, it just means, does it kind of connect everywhere? Like this one, this graph definitely does not connect everywhere. So this would be considered discontinuous, right? Like if I started here, I'd have to jump up to go there, and then I have to jump up to go there, and then I have to jump up. That's discontinuous. And then just using the graph to answer a few function questions, if I just went to 3, right, out here, and I wanted to figure out what the value of the function is at 3, I would just plug 3 into the x squared part, right? So I don't know if I have enough room down there, so I'm going to do this here. So f of 3 would just be 9 plus 6 plus 3, which I just get by plugging into this bottom part, because that is, 3 is bigger than -2, so you can plug it into that part for this function. And then what was that? 15, it's going to be 18. And then kind of similarly, -4 would be in the first part, right? Because -4 is less than -2. It's like, we could even see it from the graph. 1, 2, 3, 4. Right here, it looks like it's 1. So we're going to get a 1 for that. And we already did f of -2. F of -2 was 3. And that is about it for this problem. I just want to do one more, just using the weird kind of step function that we saw over here. I just want to graph one of these just so you kind of see how we can change this graph around. It's kind of a